The potential costs due to equipment damage, interruption of power, and associated safety issues give a high priority to protection. For example, if a small section of aging insulation in a large distribution transformer fails, high levels of fault current will flow. If the fault isn't isolated quickly, the fault current will cause the conductors to heat. As the temperature of the conductor rises, the damage will spread to the surrounding insulation, causing it to fail, and the fault current will increase even further. As the level of fault current increases, the temperature will rise to a level that will melt the conductors and burn the steel laminations, resulting in catastrophic damage to this inadequately protected transformer. There are many causes of power system faults: lightning, wind, and ice and snow, just to mention a few. The protective system must be able to sense the fault and take appropriate action within a time frame necessary to minimize damage. Faults may be intermittent or permanent in nature. Lightning striking the transmission line or a strong wind causing two phases of the transmission line to touch and form an arc are common causes of an intermittent fault to an overhead transmission line. The resulting arc ionizes the air and turns it into a conductor. The arc is then maintained by the power in the line. In both cases, the protection system responds by removing power from the line for a period of time long enough to allow the ionized air to dissipate, and then reapplies power to restore service. Physical damage to a power system component, such as the transmission line or towers, are two examples of permanent faults. The protection system must be able to quickly sense and isolate the faulty components to minimize damage. There are many sources of electrical power: gas, nuclear, hydroelectric, and alternative. The electrical power that is generated by these sources must equal the power that is consumed. Let's take a look at a simple system consisting of a generator, steam turbine, prime mover and control system, and a residential load. As stated, the generated power must equal the demand, which is constantly changing. As the load increases, the generators would tend to slow down, resulting in a reduction of output voltage and frequency. The generator's control system will sense this and input more mechanical energy to match the increased load. If the demand decreases, the generator will speed up. The control system senses this and then takes appropriate action to reduce the mechanical energy input into the system. Once generated, the voltage is fed to step-up transformers for transmission to reduce the I²R losses, and then at the substation it is stepped down for distribution. Given that the power loss during transmission is equal to the current squared flowing through the transmission line times the resistance of the transmission line, the step-up transformer increases the voltage level, thereby reducing the current, resulting in an overall reduction of power loss during transmission. The Institute of Electrical and Electronics Engineers, sometimes referred to as the IEEE, have divided voltage systems into low, medium, high voltage, and extra high classes. Low voltage systems are below 1000 volts. Medium voltage systems are between 1001 and 100,000 volts. High voltage systems are between 100,000 and 230,000 volts. And extra high voltage systems are considered to be any system above 230,000 volts. The voltage levels may vary in different parts of the world, but the names of the classes for the most part remain consistent. The three-phase power travels from the generating station over high power lines to substations. Different voltages are required for residential, commercial, and industrial customers. And so, at substations, breakers and transformers route and step down the voltage to a suitable level for distribution. Let's take a look at a typical distribution system for a residential customer. Let's recap. The generated power is transmitted via high-power transmission lines to a substation, where it is stepped down and routed to residential users. From the substation, the residential power lines take the power above or below ground to a transformer, which steps the single-phase voltage down to a suitable level for home use. From the transformer, the power then enters the home through a metering device and is then routed to a load center. From the load center, power is routed to different areas of the home. The distribution system for a typical industrial or commercial user shares some similarities to that of the residential customer, with the major exception that the power being delivered is usually three-phase. From the substation, the industrial or commercial power lines take the power above or below ground to a large transformer, which steps the three-phase voltage down to a suitable level for the plant or building. For larger commercial or industrial users, this voltage may be in the medium voltage range. In this case, there will be an additional substation on site. The power would then be routed from the transformer or transformers via medium or low voltage switchgear to different areas of the plant or building for further distribution via switchboards and panel boards. The power system can be thought of as a chain, the links of which are the generators, the power transformers, the switchgear, the transmission lines, the distribution circuits, and the loads. The arrangement of these links are as shown. The failure of any link destroys the capacity of the chain to do the work for which it was intended. One way in which the continuity of the chain can be preserved is to provide alternate links. For example, the transmission lines, being exposed to the natural elements, are much more vulnerable to short-circuit faults than the power transformers and switchgear. Hence, alternate transmission lines may be economically justified, whereas alternates for the power transformers and switchgear would not. The network of power systems now blanketing North America are often interconnected at various points to accomplish this. Since each link in the chain involves a large investment in equipment, alternates are frequently prohibitively expensive. To ensure both maximum return on the investment and to provide reliable service to satisfy customers, the whole power system should be kept in operation. This is accomplished in two ways. The first is by the specification of the design and the maintenance of each component of the power system to prevent a failure which would affect the component's usefulness in the power system. The economic considerations of design and maintenance procedures will allow this to proceed only so far. The second procedure which is followed is to control and minimize the effects of any failures that do occur. This is where the protective relay fits into the power system. The protective relay is the device which operates to disconnect a faulty part of the power system, thereby protecting that part and the remainder of the system from damage.